Camber Cautions. Don't over-camber beams with shear studs. Depending on the method of concrete placement, over-cambering may result in the heads of studs protruding above the top of concrete. We did a job a number of years ago. It was a big hospital facility, and this was the floor above an operating theater. And you know, if you've seen the movie, you know, you have the up above, you're looking down through a big opening so you can sit up above and look down on the operation. And so there's a big square opening in the middle of this floor system. And unfortunately, every member in that whole framing system all the way around there had cambers in it. And when we got to the center of that opening, and the fact that you didn't have all that dead load because of the opening out there, I think we were something like about 2.5 inches high with camber. And we had studs that were sticking up out of the floor, basically. And we ended up having to cut a bunch of them off. But that's a concern you have. You have to be careful about camber differences between beams and joists. Joists have standard cambers in them. You have to be careful of doing cambered beams or joists adjacent to non-cambered supports such as moment frames and end walls. This creates problems. We'll talk more about that with relation to decking on these issues. The AISC Code of Standard Practice, now in not the current 2005 edition, but the previous edition, which I believe was like 2001 or 2000, for the first time included camber tolerances in the Code of Standard Practice. Previously, this was in the manual, but was not in the Code of Standard Practice. And the camber tolerances that are in the Code of Standard Practice are basically it's -0 plus 1/2 inch for most beams. And if you're over 50 foot, there's some additional increase that you get. But the thing I always try to tell people is that you should remember that these tolerances are really workmanship guidelines. You don't have to consider these things as absolute issues. I tell our people in the shop when they're cambering. Now, again, maybe I should talk a little bit about the cambering process so you understand some of the problems. Like I say, you put these beams in the machine, you shove them through yield, you back off, you have to see how much set it's taken. Now, if you've got a number of beams alike, they'll generally perform fairly uniformly, but there will be some differences. And it's hard to exactly control the machine. You have a little gauge for the amount of deformation you're doing, but what you end up doing is you hit the beam, you get what you think is the right amount of camber in the machine, then you end up stretching a string line from end to end and coming in with a tape and measuring the mid-ordinate. That's typically the way it's done. It's not a very precise method of doing it. And what I'm telling our people is that, hey, I want you to get -0 plus 1/2. I said, but if you're doing 10 beams and you got one of them that instead of it's -0, it's -1/4 of an inch, I'm probably not going to make you put that thing back on the machine, depending on the amount of camber in it. I mean, if you're talking, you had 2.5 inches of camber specified and you ended up with 2 1/4, probably not going to be a big issue. If you end up with 1/4 inch more, it's not going to be an issue. But I want the majority of our members to fall in that range, because it's not really going to make any difference when you go out there and put your deck on that thing and start pouring the floor. But that's a guideline that you're looking for. It's really a workmanship guideline. And again, like I say, the AISC Code of Standard Practice indicates that camber is to be measured in the unstressed position in the shop. People talk about, do you lose camber in shipment to the job site? And that's an issue I don't know that's ever been resolved, whether you do, and maybe in certain cases you can lose it. Years ago, when I first did my paper I ever did on camber, it was a gentleman, I think it was Larson from Bethlehem Steel, did a study at that time on camber loss. And he did determine that there was some camber loss, although it was never really sure because measuring the camber in the mill at that time was not that accurate a thing either. So he didn't know how good his measurements were originally when he tried to compare them in the field. But generally speaking, I haven't found a significant camber loss in shipping. And so normally anything you're going to lose is not enough to create a problem. I sometimes think that if you had some very light members, again, like I say, some very light members, and you were doing 100% composite where you're shooting a lot of studs on top, I think you could have some problems that way. Steel deck does not bear on support. The contractor cannot make deck bear on adjacent support. This happens when you have fill-in beams or trusses with large cambers adjacent to beams or trusses with less camber. And beams or trusses or joists with large cambers are adjacent to deck walls or angles on concrete or masonry bearing walls. This is a common problem with joists. We have a job right now in Chicago here out in Rosemont that the engineer came up with a detail because he's got relatively long span joists adjacent to a wall. We've had this problem occur where we've had moment frames, and the moment frames have been parallel to fill-in beams, and the moment frames have had no camber in them. And in that particular job, we had a cellular deck on it. We have a gentleman here from HGA, and it happened to have been an HGA job we had it on. And we ended up having to, well, the solution to it here is that to saw cut the deck is what we did. And you sort of hate to do that on cellular deck, but it was necessary in this particular case. And then deck becomes a simple span rather than continuous, which is okay provided it's got the strength and deflection requirements. And the prevention is to design for these conditions. You might transition changes in camber or provide for a deck splice. This brings to mind the fact that, you know, a lot of us, when we're doing office buildings, a lot of times they're spec-type buildings. And then as you're in the process of fabricating and erecting these buildings, they lease space and they do tenant build-outs and stuff like that. It's not uncommon to come back in and put floor openings in after the fact and stuff like that. And one of the things that you got to remember when you're doing that is that you might be creating single-span deck conditions. I had a job that way where we had a condition that we modified a floor opening. We created a single-span deck, and the deck was already at a marginal condition. And fortunately, on this particular job, the general contractor got some shores under that span after the deck had deflected about 2-3 inches. He didn't lose the piece of deck. But you know, anytime we start modifying openings and changing our deck conditions, you know, keep in mind that you should go back and look at your deck and make sure that it'll work as a single span condition. What to do about extra concrete due to beam deflection? You reevaluate the beam strength to determine if it can support the additional weight. Maybe reinforce the members. We had a project we were doing. It was a medical facility, and the designer and the architect and the structural engineer on the project decided that they were sort of concerned about vibration, and they decided to use normal weight concrete. Almost everything we do in most composite floors nowadays are lightweight concrete, but they decided to go to normal weight concrete. So not only did you have the additional weight of the concrete, you had another 1.5 inches of concrete on top of it because you needed it for fire ratings. So I can't remember what we had, but it was, you know, 7 inches or something like that of normal weight concrete. And the beams were not cambered on this particular job, or if they were cambered pretty minimally. And the general contractor was under directions to pour a level floor. And so they went out there and they started putting concrete on it, and the floor deflected. And so they put a little more concrete on it, and they, you know, it deflected again. And anyway, when they finally got it, fortunately the beam stayed up, and they finally got done. They found they had, you know, 3.5 inches of additional concrete out in the middle of some of these spans. And the erector got a nice change order to go back and weld a bunch of cover plates on the bottoms of these beams and stuff like that. So, you know, that's something to keep in mind. We always, this says provide notes on drawings about the need for extra concrete. I don't know that I've seen it that much lately, but I remember in the early days of composite construction, some of the general contractors would figure their concrete volume on the theoretical thicknesses, you know. And then when you had some deflection in your deck and you had some deflection in your beams, and they had additional concrete out there, they were going back and trying to claim an extra for it. I don't know that that's common, but we used to see notes on there that they had to provide concrete, additional concrete to compensate for any deflections and that. Again, like I say, provide camber to avoid this thing. Use stiffer beams and design beams for extra concrete. You know, Jim talked about design guides on the AISC website, and that's one of the things we always like to give plugs for is the AISC website. There's just a wealth of information in there. And this whole issue of level floors and ponding of concrete and stuff like that, there's an engineering journal article a number of years ago by John Ruddy on level floors. And you may want to go on site and dig that article out, because he talks about this whole ponding issue and other things to do level floors. And I will talk a little more about level floors as we go along here. If a floor is not level, you might be able to use latex leveling compound to fill it in, or you can grind off high concrete. I don't know how it is nowadays, but I know that in the early days of lightweight concrete, some of these leveling compounds didn't adhere that well to lightweight, but I think they probably solved that problem now. But the prevention is to camber the floor beams to compensate, increase the concrete volume by varying the slab thickness, use larger beams, or use laser screed. We have a very good customer of ours who I've worked with for almost 40 years, and I've seen him grow from a 3 or 4 person office to a company that has offices in Minneapolis and Phoenix and Tampa and Chicago and I don't know where else now and that. And we've done a lot of office buildings with them, and we did a series of some of their first mid-rise, high-rise buildings in Minneapolis. And they were doing Class A structures, and in some of the Class A structures you had doorways and door frames that went up to the ceiling level. And of course the problem you had is that you'd come in and set a ceiling level, and if the floor over there varied, your door frame didn't meet the ceiling level quite right. So it was important to have level floors across this whole area to make these architectural features work. And on the first building they did a lot of work grinding and filling and stuff like that. So on the second job they said, well, we're going to laser screed this job. We're going to get level floors. And so fine, and they laser screeded, I believe, the second and third floors. And then somebody went back and checked the floor slab thickness, and the floor slab's thickness was no longer adequate for the fire rating, and had to go back and spray the underside of the deck because some of the cambers hadn't come out as calculated. And so that laser screed went by the wayside. Now these people have learned through practice to do very good level floors. But they talk with the structural engineer. They talk about the amount of camber they're going to get, how much deflection they're going to get. They talk with their field crews about concrete placing methods, how they're going to put their screeds, their fabricator about their cambers they're going to have. They look at the whole construction process, and as a result of it, they do get good level floors. But it's a total construction process that you have to go through to get the level floors. Shear studs. Studs break off during inspection. You can inspect and replace. You can fillet weld studs if only a few are required. Prevention, you want to install studs properly. And you've got AWS section that talks about the qualification requirements. The manufacturer qualifies the studs generally for the deck. That's a requirement. Again, like I said, that somebody mentioned I'm part of the AWSD 1.1, one of the subcommittees, and the manufacturers tried at one time to shove this qualification requirement downfield and put it in the field because they said, well, there's so many different deck requirements and stuff like that. Fortunately, D1.1 did not listen to them and say this is a stud manufacturer's requirement to design and develop the stud that'll work under these different conditions. Troubleshooting stud installations. Nice things about studs is they're relatively foolproof type things. I mean, they're simple, and if you got problems, you can usually figure out what the problem is. First requirement is you got to have surfaces that are clean and dry. You know, dry in particular, you know, is important. Then you need the proper arc shield or ferrule for the job. In other words, are you shooting through galvanized deck? Are you shooting through painted phosphatized deck? Are you shooting to bare steel? There are different ferrules required, so you want to have that. The next thing is you got to have enough power. You got to have enough amperage so you can build that arc and get that puddle and shove the thing down. Then your welding gun has to be set up. The timing has to be right so that you withdraw the stud, you create your arc, and when it's just right, plunge the stud into the arc pool and that. The gun has to be held in position nice and straight until that weld is solid. And then after you pull that off, you break the ferrule off, you want to look at it, you should have a 360-degree weld flash all the way around the bottom. And, then you can either bend a few initially for the day probably, or else you can ring them to see if they're looking good. But the nice thing about that is that if you do have a few studs that are bad, you miss it for some reason or other, if you go run the numbers on composite design and there are a few studs bad, it changes such a small percentage of your strength of your member that it really doesn't affect your overall strength that much. So if you do have a few studs that are bad on there, I wouldn't lose any sleep on it. Okay, fillet welds on studs. AWS has a procedure for fillet welding studs. And for fillet welds, the stud base shall be prepared so the base of the stud fits against the base metal. If you've looked at a stud, there's a little protrusion on the bottom of that stud. And it's needed for when you do using the stud welder on it. But if you're going to fillet weld them, what you want to do is you want to hit that base of that stud with a grinder so it sits down tight and you can get a good weld with a big gap, without a gap down there. Again, I'm not a big fan of fillet welding studs. I have seen a major failure of some embedded plates that were fillet welded studs. It was a combination of things, like anytime you have a failure, there's more than one thing that's happening. This job was there was a parking ramp, probably about 5-6 stories, and it was like an open donut. There's a big square in the middle, and it was a government parking ramp, and they decided that they were getting all this snow up there in Minneapolis into this thing, so what they wanted to do is put a cover over this big square opening to keep the snow out, and then they could also park on top of this to get some extra parking spaces. And since it was it was sort of like a patch-on, instead of having a regular fabricator, they got a miscellaneous metals guy to do some embedded plates when they raised the concrete columns up. And he didn't have a stud machine, so he fillet welded the studs on. And then the detail of the plate to the beam connection to this put some moment, as Jim talked about, into the plates. So now you had not only straight shear on the thing, you had some moment on the plates. And one day this thing collapsed. The whole thing came down 6 floors straight down in one unit. Fortunately, it was Good Friday afternoon and all the government employees were off, so nobody got hurt in that. But again, fillet welding can be done, but it needs to be checked and done right. And AWS will also give you the minimum weld size. Studs too high, you can remove the studs and replace. You might get by with using additional concrete thickness. You could perhaps take some beam camber out by heat straightening. We've never used heat straightening in the field for something like this. We've used heat straightening in the field when we've had special architectural members that were maybe curved and we had to do some adjustments. But even there, when you're doing that, normally the erector is not familiar with how to do it. You either have to get a specialist in, or the fabricator who's familiar with it would have to write a very detailed procedure and help supervise the erector to make sure it's done right. But generally speaking, you'd probably either remove studs or use additional concrete. Prevention is specify camber properly and select stud length and mid-range. The LRFD specification did not have a minimum stud cover requirement over the studs. The old ASD, or the old previous composite requirements, had a requirement for 3/4 inch cover over the top of the stud. The 2005 specification does have a requirement for 1/2 inch cover over the top of the studs. It's just good workmanship. It's a workmanship problem. It's not a structural problem, but it's a workmanship problem. And I think if you look at your slab thickness and you look at your deck, the depth of your deck, you'll find that there's quite a range that you can put in there. You're required to have the stud, I don't know, like 1.5 inches above the top of the deck, and then if you have to have it a 1/2 inch below the top of the concrete, there's probably at least 1 inch variation in there. And so the ideal thing is to, when you pick your stud size, try to pick something in there so that you've got some, you've more than got the amount above the deck, but you got some room in case you have some camber problems that your stud won't be projecting up. So try to pick studs that are in what I would call the mid-range, between the maximum and minimum that you can use on that stud. Fabrication and erection. This is a wonderful job. This happens to be Millennium Park. You can see this is the end of about a 110-foot cantilever truss, and these are a whole bunch of connections out here, and these are some connections for some of Frank Gehry's wonderful curved panels. We finally settled the lawsuit, so I guess I can talk about it. By the way, I know a few people are familiar with Prairie Home Companion out of the Twin Cities and Garrison Keillor. Garrison Keillor just made an announcement, I believe 2 weeks ago, that Prairie Home Companion is now offering a Frank Gehry melon baller. So when you do your fruit salads, you can cut all those wonderful curved shapes that Frank Gehry has so good, and so your fruit salads will now look like an architect-designed fruit salad. So contact Prairie Home Companion if you want a Frank Gehry melon baller. Anyway, we're going to talk about some fabrication issues. We're going to talk about incidental corrosion on steel needs to be removed. Yes, and we're talking when there's incidental corrosion, we're talking basically rust, loose scale, and, well, not just rust. Yes, if paint's going to be applied. No, if fireproofing is going to be applied. Again, if the rust is tight, you don't have to worry about it. If you're going to paint, that's a different issue. And we're going to talk about, just very briefly, about some paint problems. You know, as fabricators, we don't like to paint. We'd much rather send out bare steel, and the vast majority of our stuff can be sent out without any paint on it. Anything that's enclosed in building finish and anything that's going to be fireproof should not be painted, you know, and that's a lot of material. Anything that's going to be inside of building and not exposed to weather can probably just be an SP2, a hand tool clean, and a standard primer on it. If you've got some special architectural finish, you might do something different. But there's a lot of stuff that can go out unpainted, and quite frankly, if you're an environmentalist, why contaminate the thing putting paint on it and having paint on the steel? There's no reason for it. Anyway, some of the problems you've got mill scale lifting, paint lifting, run sags, mud cracks, pinholes, and chipping. These are all little issues, and these are some of the problems, the reasons for them, and we'll talk about them. The first one, mill scale lifting. This is when you typically have an SP2 or an SP3 clean. That's hand tool or power tool clean. There's really no difference between hand tool and power tool. The cleanliness is still the same. You have to remove loose scale is the intention, and any loose rust. That's what you're trying to get off. And so SP3 is really not any better than SP2. The results are the same. And that's adequate for, you know, if you're doing a warehouse or industrial building that doesn't have corrosion in it, the SP2 is fine. And if you have scale lifting, it's probably because you didn't get the loose scale off. If it's exposed to weather, that's a whole different animal. You know, the prime paint that we put on over an SP2 is supposedly good for only short-term protection. And if you're going to have any additional protection or appearance, you need to paint over it. Problem you get into is that people try to think that the primer is going to be a finished coat. I had a project, Corps of Engineers project, a hospital up in the Upper Peninsula of Michigan, or as people in Wisconsin would say, a UP, a UPER. It was an Air Force Base hospital up there, and we had prime painted the facility, and I got a call from the Corps of Engineers saying that your paint's not standing up. And we said, well, it was only a primer, but I went up to see what the situation was. Those of you that are familiar with the Upper Peninsula of Michigan know they get about 250 inches of snow a year. And this was in the middle of the winter, and they had a roof that was sloping for internal drains, which really weren't in place yet. And they had roof deck on it, but no roofing. And they had heat in the building. So every day it snowed, and every day the snow melted on that roof and ran down the joints and ran around our beams. It was like it was encased in a waterfall constantly. I just looked at it and I said, and you expect our prime paint to stand up under that? Actually, the thing is it was all going to be enclosed in building finish, you know, so it didn't matter anyway. But so that happened. Paint lifting, that's usually a matter of some sort of contamination on the surface. Quite often, some sort of solvent or grease on the surface. We've had this problem happen to us on HSS. If you're familiar with the HSS process and how HSS is made, what you have is a big coil of steel, and the coil is unrolled and slit to a certain width, and then it runs through a whole series of rollers that form it up, typically form it up into a circle, and then that weld, the seam is welded, and then it goes through a whole other series of rollers that form it into the rectangular shape that you're probably going to end up buying. And of course, all these rollers and stuff have forming lubricant on them and stuff like that. So HSS comes out, even when you try to buy it bare as a fabricator, it's got something on it. So typically it needs to be washed down or cleaned down, or some care to have this solvent clean, which we call an SPC1, which is solvent clean. And the third one is runs and sags. And here the problem is that you might have to reduce the coating thickness or use high solids. You know, whenever you specify paint, stay within the manufacturer's requirements. You know, if the manufacturer says you should be putting 2 mils on or 2.5 mils on, don't try to require 3.5 mils or something like that, you know, because there's a reason why they do this. The other thing is there's a difference between painting surfaces, for instance, between painting a rolled beam that has been hand tool cleaned, it has mill scale on it, type mill scale, versus an HSS, which virtually has no mill scale on it, has a smooth surface. And when you're painting the wide flange, you want something that has a vehicle in it that will allow this thing to flow and go over all these little irregular surfaces and fill in all these things on the wide flange. When you got an HSS, if you have that same thing, it's going to run and drip and sag. And so the solution probably is when you're doing an HSS, you adjust and use what we call less vehicle, use a high solids type paint, and then you can build it up. You use that same high solids on a wide flange, and you probably will have some holidays, and you might have some rust bloom coming through pretty quickly. The last three are generally with more sophisticated paint systems. Typically with using inorganic paints, which is a very good paint. Inorganic zincs are, fabricators have a love-hate relationship with inorganic zincs. It's a high-performance paint and gives very good corrosion resistance, but it is very, very difficult to top coat in the shop because it takes a long time to cure, and it takes moisture to cure. I mean, you look at the research results and they say that you really should be having this thing in like 100% humidity for several days. And when we're doing it like in Minneapolis and we've got in the middle of winter and we've got a heated shop, you know what our relative humidity is. And you almost have to spray this stuff with water to get it to kick over. If we don't have to top coat it, it's a fantastic primer, really does a good job. If we're going to have to top coat it, we'd much rather use an epoxy zinc. And the epoxy zincs you can put on almost wet on wet, and they give you almost the same performance. In fact, will give you better because you don't have the other problems. We're talking here, when you're talking about mud cracking, this happens because you overbuild the coating. When you when you spray paint material, the idea is that you're supposed to take your spray gun and hold it, you know, approximately 2 foot away from the surface and keep it at 90 degrees to the surface, because you don't want that paint impinging and bouncing and stuff like that. So you'd like to keep it so you'd walk down the surface. Well, the problem is painting the inside of the flange. You can't do that when you paint the inside of the flange. You got to paint at an angle. So you tend to bounce down and hit the web, and then when you paint the web, what you end up is, so in that fillet between the flange and web, there's a tendency to the underside of the web tends to either get underpainted or the fillet gets overpainted. And if it gets overpainted, and when it sets up, you'll get what looks like a mud crack in there. Now, fortunately, you can generally just sand this stuff down and reduce it and get rid of it that way. Pinholes is when you try to top coat the inorganic zincs with an epoxy before the inorganic zinc is fully cured. And so what happens is some of your gases are trying to come out of the inorganic zinc, and it forms little pinholes in your epoxy. And then finally, the chipping is what happens is that if you don't get pinholes, if you're cured enough, you probably still don't have full strength in that zinc layer down below, and you put this high build epoxy over it, and that sets up real hard. And as soon as you bump it, what happens is that shears right in the zinc layer, and the epoxy will come off, and you'll have a little bit of zinc on the back side of the epoxy. You can even have situations where if it hasn't been properly cured, later on you can have thermal stresses in the field, and just the thermal stresses may cause this stuff to shear off through the zinc layer if the zinc is light. So again, like I say, as a general rule, inorganic zincs are great if you can leave them and then top coat them in the field after they've fully developed their strength, and we've done that, and it's been very successful on roadways and stuff. Otherwise, if you want to put a second coat on in the shop, generally you should use the epoxies. Keep moving along here. Boltstone